Hello, everybody. Professor Barlow, Physics 215, Physics for Scientists and Engineers, Calc-Based Physics, Northampton Community College. We're going to be going over Chapter 20. This is the last chapter for the semester. This is the last chapter of the material you're going to cover in this class. Some of you will be taking Physics 225, the second half of the physics. Some of you, depending upon the branch of engineering you're going to be going into, may or may not need 225. That, depends on you. It also depends on if you're going for the degree here at Northampton, whether or not you need 225. It's a relatively short chapter. The calculations compared to most of where we've been are pretty light, pretty easy. A lot of theory, and a lot less calculations. So with that, let's get into the last chapter of the semester. So we are going to be going over the second law of thermodynamics. Okay, so we're going to introduce what that second law is. We're going to talk about heat engines. There's going to be some calculations that we're going to be doing with heat engines and their efficiencies. We're going to talk about reversible and irreversible processes. We're going to talk about a Carnot engine, refrigerators, air conditioners, and heat pumps. We're going to talk about the concept of entropy. Some of you might find that to be a bit of a review. We're going to go over how entropy and the second law of thermodynamics are related. We're going to talk about how order goes to disorder. And the last thing we're going to talk about is availability of energy and something called heat death. The last three topics that you see there, we're not going to cover in this class. Depending upon what type of engineering degree you're going for, you may spend an entire class on just thermodynamics. Like I said, with some of the other chapters, we're just scratching the surface on some of these topics. Statics, fluids, thermodynamics, all of those things are going to have a full 16-week semester-long class that you're going to dig deeper into and get more detail on it. So the first law of thermodynamics told us that energy is conserved, okay? In the absence of the picture that you see above, okay, just the idea of the conservation of energy isn't the whole story. If you were to run those pictures in reverse, it wouldn't look quite right? So the order matters. The process is important. Heat doesn't flow backwards. Heat doesn't go in reverse. Water doesn't flow uphill. Things don't fall upward unless, you take the video and run it in reverse. Another way of looking at it is if you take salt and pepper, an equal amount of stuff, put them in a container, shake it up, it doesn't matter how much you continue to shake it, you're never going to separate those back out on their own, okay, but just by doing that same process. So that's kind of, an abstract introduction to this. The second law of thermodynamics is a statement about which processes occur and which don't. So there's many ways to state it. The book's definition is heat can flow spontaneously from hot to cold. It will not flow from cold to hot. Spontaneously meaning on its own. Now that doesn't mean we can't sort of influence things, okay? So it's easy to produce thermal energy using work, right? You can produce thermal energy by a campfire. A campfire is, you're creating thermal energy. The picture that you see is an illustration of a heat engine. Mechanical energy can be obtained from thermal energy only when heat can flow from high temperature to low temperature. So Q high is going to be equal to work plus Q low. Right? And just be careful, because in that equation, not all of those values are going to be positive. Okay? So we'll discuss engines that run in repeating cycles that just constantly do the same thing over and over. The change in internal energy over a cycle, over a complete cycle, is going to be zero as the system returns back to its initial state. The high temperature reservoir is going to transfer an amount of heat, we'll call it Q high, to the engine, where part of it is transformed into work and the rest is a Q lower temperature, which goes back to the beginning or is exhausted to the lower temperature reservoir. All three of these quantities in this type of engine are positive. I'm sorry, when I said back here, not all three are going to be positive. When I was on this slide, I said they're not. That was an error. Okay, all three values are going to be positive. Okay, so a few examples of heat engines, right? Steam engine, very early form of heat engines. Reciprocating type, so you have temperature, water at a lower temperature. Okay, it you heat some sort of heat input, some heating element. You have water in a boiler and you heat that water, it becomes steam. It goes down through some valve, it moves a piston. You connect this to something. Are you generating electricity? Are you moving a train? You're doing some sort of work. And then that water will recondense back to lower temperature and you go through the whole cycle again. Okay. There's other ones, turbine. Okay. You have a boiler on a condenser, which isn't shown. You have high pressure steam, which is rotating a turbine. The low pressure is exhausted to a condenser. Okay. So two different types of heat engines. Internal combustion engine is a heat engine. So you have the different cycles of an internal combustion engine. You have intake, which your fuel and air are going into the cylinder. Starts compressing. You compress it, a spark ignites. That spark expands and pushes the piston back down. And then you exhaust out the spent gases and you go back to the beginning to the intake cycle again. And those pistons spinning turn the crankshaft, which eventually at the tail end of that turns the tires. Okay. Why does a heat engine need a temperature difference? Because the work done on the system in one part of the cycle would be equal to the work done by the system in another part, and then the network would be zero and you're not accomplishing anything. So the efficiency of a heat engine, this lowercase e, right, is the ratio of the work done to the heat input or the heat high. So conservation of energy, right, if you want to eliminate W, right, work, if we rearrange the equation, now let me write this up on the whiteboard so it's a little easier to see the idea or the concept of it. What we were saying earlier is Q high is equal to work plus Q low. If I rearrange this to solve for work, okay, if I want to get work by itself to substitute into the other equation, that was on the slide, it's going to be Q high minus Q low. So we started off with lowercase e being efficiency, right? Not lowercase e from calculus, not natural log. Script D for efficiency. Q over H. Now I'm going to take this and plug it in for this W, and we're going to get QH minus Q low divided by QH. I could rewrite this to also be equal to 1 minus QL over QH. So on your equation sheet, you can have both of those. Okay. So let's take a look at an example. You have a car and we want to determine efficiency. So you have an automobile engine, has an efficiency of 20%. Okay. It produces an average of 23,000 joules of mechanical work per second during operation. They want us to determine A, how much heat input is required. And they also want us to determine how much heat is discharged as waste heat from the engine per second. Okay, so we are going to back to the whiteboard and use the equations that we just figured out here. Right, so for part A, I'm going to take this equation right here. E is equal to work over QH, and I'm going to rearrange it. Because we were given efficiency, but we want to know for part A how much heat input is required. That is your QH. So I'm going to solve for QH, and I'm just going to flip-flop my E and my QH. So I got work divided by efficiency. So my work is 23,000 joules. Efficiency gets entered not as a whole number percentage, but as a decimal. So 20% is 0.20. So part A, Q high, is 115 kilojoules, or 115,000 joules. So B, we want to determine how much heat is discharged as waste. So we're determining QL. Okay, we want to know QL. So if we take a look at this equation right here, we were given efficiency. We just determined QH. All we need to find is QL. So E 1 minus QL over QH. So it is 0.20. 1 minus QL, that's what we're determining, 115 kilojoules. We rearrange this and just solve for QL. QL is 92 kilojoules, is how much heat is discharged, as waste heat from the engine. No heat engine can have an efficiency of 100%. It's not possible. This is another way of writing that second law. So remember we said that we talked about different ways of saying the same thing. Another way of saying the second law of thermo is that no device is possible whose sole effect is to transform a given amount of heat completely into work. There is going to be some loss there. Okay. The little picture that you see below, it's a schematic of a hypothetical perfect heat engine where all the heat input would be used to do work. And that's just not possible. It doesn't exist. Okay. We're going to talk now about reversible and irreversible processes and the idea of a Carnot engine. A Carnot engine was created to examine efficiency of a heat engine. Okay. It is an idealized concept. It is not real. The reason it's idealized is because there's no friction in it, which again, not possible, not physically possible. So each leg of its cycle is reversible. So what do I mean by reversible? I mean very slowly. So each step is a series of equilibrium states, which could be done in reverse with no change in magnitude or heat exchanged. So that's what I mean by reversible. Irreversible is some sort of turbulence, whether it's a gas, friction, whatever. Irreversible, there is some sort of friction or something. Okay, so the Carnot engine, it has four basic parts. Okay, so four basic things are happening. In part one, you have an isothermal expansion. So part one on this thing is right here. It's from A to B, right? It's number one. The gas is first expanded isothermally with the addition of Q heat, okay, along path AB. So from A to B is step one or process one. It's an isothermal expansion. From B to C, no heat is exchanged, but the temperature drops from a high temperature to a lower temperature from B to C. Process two, pardon me, is adiabatic expansion. Process three goes from points C to D. This is where the gas is compressed at a constant temperature, okay, and heat flows out. Okay, so heat goes out of the system. And the last step, which gets us back to our beginning, is the gas. So process three is isothermal compression. The last step is adiabatic compression, right? So finally, the gas is compressed adiabatically from point D to A. Step four, adiabatic compression. So it's a theoretical idea, and it helped play an important role in the development and the concepts of thermodynamics, okay? So it's important in terms of concept, just recognize that it's sort of an idealized perfect world thing. So for an ideal reversible engine, the efficiency can be written in terms of the temperature. So the ideal efficiency, 1 minus TL, the lower temperature, over T high, we see that 100% efficiency can only be achieved if the cold reservoir is at absolute zero, which is completely impossible. Real engines are going to have some sort of friction loss, and the best ones are up around 60 to 80%-ish of a Carnot value efficiency, okay? So another way to look at this in the previous slide, we said E ideal is 1 minus temperature low over temperature high, which would also be equal to 1 minus QL over Q high. If we look at a Carnot engine, you're looking at a ratio of QL over Q high, TL over T high. Notice in both of these, this one and this one, the units for temperature are in kelvins. Okay. So again, for a Carnot engine or a Carnot cycle, okay, so we want to test an engine manufacturer's claim. They're saying that they make an engine that conforms to the following specifications. The heat input on this engine per second is 9 kilojoules at 435 Kelvin. The heat output per second is 4 kilojoules at 285 Kelvin. Should we believe this claim? Okay. Well, let's go back to my whiteboard. And take a look at the ideal efficiency. Okay. Ideal efficiency is going to look at the temperatures. So E ideal, 1 minus 285, whoops, 285, not 28. So 285 Kelvin on the low end. On the high end, 435 K. So when you get this, you're going to get an E of 0.34, which is 34% efficient. Now remember, this is ideal because we're using the temperatures. Now let's take a look at the Q that they gave us. So E, looking at the Q, so now I'm going to look at the heat that not the temperature that they gave us, but the heat transfer that is happening. You have 4 kilojoules in the numerator for the low, the QL, the Q high, 9 kilojoules. So based on what they gave us, based on Q, E is 56, which is 56% efficient. What they're reporting is greater than ideal, and ideal basically tells us that it's not taking into account friction or anything else. So you know, because they're saying that they're more efficient than this ideal, that they're lying, that it is a false claim. Okay. Okay, automobiles run on an Otto cycle, OTTO. There's 2 adiabatic paths, to constant volume pass. This isn't going to be on the test. Gas enters the engine at point A down here. Okay, is ignited at B. Curve CD is your power stroke, and DA is the exhaust. Okay. The ideal gas, the efficiency for an Otto cycle is given by this equation. Again, it's not going to be on the test. We're now going to talk about refrigerators, air conditioners, and heat pumps. Household appliances that are heat engines. So a refrigerator is basically a heat engine running in reverse. Okay. What you're doing is you're doing work to take the heat and extract it, so you're left with the cold, okay, to keep things cold. So, you know, you're taking heat is extracted from this cold reservoir and exhausted. So if you ever felt the back of a refrigerator, particularly an older one, they get relatively warm on the outside because the coils on the back are dissipating the heat, okay? They kind of show the details of what's going on here. So you have an electric compressor motor forces a gas at a high pressure through a heat exchanger or a condenser, okay? And then the outside walls of the refrigerator, QH, give off that heat, and that's why they have those slats and the tube going up through it. It's radiating the heat away from the inside where you want to keep things cold or frozen, okay? And that's done by some sort of motor, whether it's an electric motor, which that they are. I mean, refrigerators are all electric motors, right? So with these types of appliances, you have something called the coefficient of performance, or COP. Okay, COP right here is given by, you take QL and divide it by W. It's a ratio of heat on the low end divided by work. Okay, you know that work is QH minus QL. Same thing with coefficient of performance as efficiency. You can calculate a coefficient of performance that's ideal using temperatures, and then Q just to get the standard coefficient of performance. So if you want to make ice, you're given that a freezer has a coefficient of performance of 3.8, uses 200 watts of power. How long would it take to freeze, if the freezer is empty, to freeze an ice cube tray that contains 600 grams of water at 0 degrees C? Now notice we're given the mass of the water in grams, not kilograms. Remember that most of the coefficients that we're going to look up from the tables we'll be given are in units of kilograms. So be careful that you're working in the correct units. So what we're going to do now is we're going to take a look. And we know from the previous chapter, the Q is the mass of what we're looking at. So this is latent heat of fusion. But we're going from a liquid to a solid, not from a solid to a liquid. So we were given 600 grams. 600 grams is 0.6 kilograms. We know the latent heat of fusion we're going from liquid to ice or ice to liquid, it's going to be 333 kilojoules per kilogram. So the Q that we need to convert the water to ice is 200,000 joules. That's what we need to make this happen. If we're given that the refrigerator works on 200 watts, we know that 200 watts is 200 joules per second. This is work per time. Okay. If we want to figure out the time, which is what they're asking us, we need to say that T is equal to 200 joules per second. Our coefficient of performance QL over W, if I rearrange this, right, I can solve for work is equal to QL divided by COP. If I take this and plug it in for this W, I will have my time is equal to QL over my coefficient of performance divided by my 200 joules per second. My Q, I'm going to bring down from up above. That's my 200,000 joules. Divide that by the coefficient of performance was given as 3.8. And then that whole thing divided by 200 joules per second. Time for all of this, 260 seconds. So I don't know about you, but 260 seconds, that's the equivalent of about 4 minutes, 4 1/3 minutes. I don't know about you, but my refrigerator does not make ice cubes in 4 minutes. So that's one serious refrigerator. So I don't know how realistic in the real world some of these numbers are, but that's how you would do it. Okay. So your house works in a similar fashion. Okay. You can have a heat pump in your house. During the wintertime, it's cold outside. You want it to be warm inside the house. You have a heat pump, uses an electric motor. It can be fed by, gas, electricity, coal, oil, to heat the outside cool air to warm air inside the house. Okay. In the summertime, an air conditioning system will work in reverse. You're taking the warm air inside and you're expelling it to the outside. Okay. So if you have a heat pump and the heat pump for a house has a coefficient of performance of 3, and is rated to do work at 1500 watts, how much heat can it add to a room per second? And then after we do that, part B is if the heat pump were turned around to act as an air conditioner in the summer, what would you expect the coefficient of performance to be, assuming everything else stays the same? Okay, let's take a look using our whiteboard. So rearranging our equation for coefficient of performance, we have Q high is COP times work. They gave us in the problem statement that the coefficient of performance is 3. They also gave us 1500 watts, which is the work. Watts are also joules per second. So Q high is 4,500 joules per second, or 4,500 watts. That's part A of the statement. Part B of the statement is they want us to figure out, all else being equal, what the coefficient of performance would be if this thing was functioning as an air conditioner. So to do that, we need to look at QL is equal to QH minus work. QH, they told us, all else being equal, you got 4,500 watts or joules per second minus 1,500 watts or joules per second. So QL is 3,000 watts or joules per second. Coefficient of performance is QL over work, 3,000 watts divided by 1,500 watts. So our coefficient of performance when this thing is working as a heat pump is 3, but our coefficient of performance when it's functioning as an air conditioner is 2. The coefficient of performance would be 2, reversing the inside and outside heat for the house. Entropy. So hopefully this is a review. If not, we'll talk about the concept of it. Entropy is defined as it's a measure of disorder in a system. Okay. The equation that's there is Q, or heat divided by time, or Q per time. So change in entropy, S, so S is entropy. Change in entropy is Q per time. It's a measure of disorder. Temperature is always measured in kelvins for this equation. Okay. If it is a reversible process and the temperature remains constant, your change in entropy is your change in Q per time. Okay. So any reversible cycle can be written as a whole bunch of succession of little tiny Carnot cycles. So you see this shape, it's just a whole bunch of Carnot cycles. Therefore, it is true for a Carnot cycle is true for all reversible cycles, okay? So if we have an entropy change when mixing water, okay, you have a sample of 50 kilograms of water at 20 degrees C. and it is mixed with a 50 gram, another 50 kilogram sample. So they're both 50 kilograms. This other portion or sample of water is 24 degrees C. Estimate change in entropy. Okay. So one sample of water starting at 20 degrees C, another sample of water is starting at 50 degrees C, or I'm sorry, 24 degrees C, 20 and 24. And they're both 50 kilogram samples. So how do we go about doing this? Well, the first thing we have to realize is that one of these things is going down in temperature and one of them is going up in temperature. So eventually we're going to get to the point where we're looking at change in entropy as Q over temperature. Well, to get to Q, just to get to Q, I need to look at Q MC delta T, right? So this is going to give me the heat required to go through the process of changing the temperature, the changing of the temperatures of the two samples of water. Now, we're going from one sample is 20 degrees C. The other sample is 24 degrees C. So this one is going to go up. This one is going to go down. The equilibrium temperature that this thing reaches is 22 degrees C. So this is going to gain 2 degrees, and this sample is going to lose 2 degrees. Okay. So for both of these, the amount of heat, the Q, is going to be the same because the change in temperature, my delta T, is 2 degrees. So you got that. That's rough looking. Let's clean this up a little. MC delta T. You have a 50 kilogram sample. Well, you have two 50 kilogram samples, but the calculation is going to be the same because one is losing 2 degrees, one's gaining 2 degrees. 4186 joules Kelvin per degree C. It's my C. And 2 degrees Celsius. So you get your Q 4.186 times 10 to the 5th joules. Now this isn't my answer. This isn't my change in entropy, but it's a big piece of it. Okay. It's my Q for both of these. Now remember that the temperature in this equation up here is kelvins. So if this first sample is losing 2 degrees, goes from 20 to 22, halfway in there, halfway in between, or the average, temperature average, is going to be 21. My average temperature here, if I'm going from 24 to 22, my average temperature will be 23. So my average T for the one direction is 21 degrees, which is equal to 294 Kelvin, just converting temperature. For the other average, it's 23, and that's 296 Kelvin. So now The entropy on the higher end, okay, the higher temperature sample that's going to lose the heat, right? If it's losing the heat, it's going to be negative 4.186 times 10 to the 5th joules. Its change in temperature is my 296 Kelvin. So this is negative 1,414 joules per Kelvin. My change in entropy on the lower end, I'm gaining 2 degrees. So that's 2186 times 10 to the 5th joules. This one is 294 Kelvin. I'm dividing by a slightly smaller number. If I'm dividing by a slightly smaller number, I am going to get a slightly higher answer. 1424 joules per Kelvin. But notice this is going down, so it's negative. This is going up, so it's positive. Okay. My change, so I'm going to come over here to finish this. My change in entropy is going to be the sum of my change in entropy on the high end plus my change in entropy on the cold end, or on the low side. Low, cold, you can call this cold and hot, low and cold, whatever you want to do. It's going to be the sum of negative 1414 joules per Kelvin plus 1424 joules per Kelvin. So my change is 10 joules per Kelvin. That is change in entropy of 2 50 kilogram samples of water. Okay. Total entropy always increases when heat flows from a warm object to a colder one in an isolated two-body system. Heat transfer is the same, and the cooler object is at a lower temperature than the warmer one. So the entropy gained by the cooler one is always more than the entropy lost by the warmer one. We saw that in the example. Okay. We're going to skip example 20-7. You can take a look at it in the textbook. We're also going to skip 20-8. You can look at it in the textbook. I think that the previous example illustrates it pretty well. The fact that every interaction, the entropy of a system plus the environment increases, is another way of putting, like, this is a third way of stating the same thing, right? The entropy of an isolated system never decreases. So entropy never decreases. It can stay constant in a reversible process, or it can increase in an irreversible process. So that leads us to this concept of order to disorder. Since entropy is a measure of disorder, okay, natural processes tend to move towards a state of greater disorder. So the same example of the salt and pepper shakers, you put milk and sugar in your coffee and stir it, you can keep stirring as much as you want, but you're never going to re-separate them. Okay, even if you go in a lab and boil everything away and like you can get down to the sugar maybe, but you can never go back really to the milk. So no amount of stirring is going to get you back to where you started. Another example is a tornado comes through. Okay, tornado comes through, it's going to destroy, building or whatever is in its path. It's never going to put something back together. It might plop something down in a heap, but it's not going to reassemble. Okay, and thermal equilibrium is the same. It's a similar process. Uniform final state is going to have more disorder than the separate temperatures at their initial states. Okay, that leads us to this concept of heat death. So another consequence is that any natural process, some energy is going to become unavailable to useful work. So as we move along and we look at the universe as a whole, it's going to be inevitable that more and more energy is going to be converted to unusable forms, and the ability to work anywhere is going to gradually vanish. That concept is called the heat death of the universe. Outside of physics, I would say it sounds like a pretty cool 80s death metal band, but that's that leads me to section 20-9. 20-9, 10, and 11 are asterisks chapter sections that you are not responsible for. You can take a look at them. You're probably going to revisit some of this stuff when you get into a thermo class. It won't be something that I test you on, and it won't be something that you're going to need for the final. So these graphs here showing speed versus fraction of molecule, you can see that those are bell curves, normal curves, random distributions. Most test grades are considered bell curve distributions. So another interesting thing that the book does state, and I don't want this to turn into a political argument, is they use the laws of thermodynamics to frame warming, global warming. And it's interesting because all they're doing is basing it on, what we've learned so far in this chapter. So about 90% of the energy used, that's probably changed slightly since this text was written, is generating using some sort of heat engine to drive other types of turbines. Wind, solar, they've come on and they've come a long way, but we still get a big proportion of our energy from nuclear power plants, fossil fuels, burning turbines, generators, things like that. The thermal output from all of that, the QL, the exhaust from all of that is going to contribute to warming the outside. So that warming is a consequence of thermodynamics. Summary. So this is basically the end of the chapter, end of the text, end of the material for the class. After this, after the unit 4 block is going to be the final. So heat engines change heat into useful work. We know that efficiency is a ratio of work over heat input. Maximum efficiency is 1 minus temperature on the low side divided by temperature on the high side. You have this concept of coefficient of performance for refrigerators, air conditioners, heat engines. Heat's either removed or work's done. You have a heat pump where heat is delivered to a system. Refrigerators and air conditioners are removing heat. second law of thermo, natural processes always tend to increase entropy or disorder. Entropy is a change in a reversible process. So change in entropy is the integral of change in heat, change in Q per time. So change in entropy gives direction to an arrow of time. It tells you which way the process is happening. As time goes on, energy will continue to become degraded. Heat engines cause thermal pollution. Like I said, I don't want to get into a whole political discussion about that. But on that note, that is the end of chapter 20. As I said, there isn't a whole lot of calculations. There's some, but not nearly as involved as previous chapters. That is the last chapter for the final. That is the last chapter for this class, for this unit, this fourth unit. The final exam, as stated at the beginning, it is not a cumulative final. It covers from exam 3 to now. Yes, there's going to be unit conversions on there. Come to the Zoom sessions, these last Zoom sessions, prepared with questions. Do some of the recommended problems. We went a little light on the required homework. Okay, but feel free to look at those other problems. They are good practice for the test. Get together with your classmates via Zoom or via some other Discord or Zoom or GoToMeeting, or feel free to work together in groups. You're not going to be able to do that on the exam, but work together, help each other. I'm here also. I'm happy to set up another Zoom session if the regularly scheduled class Zoom doesn't work for you. Again, you can email us questions. You can come to the Zooms with questions. With that, good luck on the final. Good luck in Physics 2. Good luck in whatever engineering degree you're going to pursue. Or if you're taking the class for another major, that's okay too. Good luck to everybody. If you need anything, feel free to contact either myself, Professor Miller, Professor Doney. We're here for you guys. We're happy to help all of you with anything you need. So good luck. Please stay in touch. Please let us know your success story later on down the line. So best of luck. Thank you for taking the class. And thank you for dealing with all of the challenges that we've had to deal with by doing these video sessions and doing things online. So we appreciate your patience. Good luck. Be well. Stay safe. Thank you. So long.